Okay, today we're going to do a little conductivity warm-up, taking into account things we learned yesterday with solubility rules and net ionics. So in the first beaker that you have, those of you at home, I'll try to give you visual cues as to what's going on. I'm going to have just water, H2O. So I have this little conductivity tester, which if there are free-floating ions in solution, it will light up. Here I have DI water. Is this going to light up my light bulb? What do we think? Woo, that's exciting, isn't it? Absolutely nothing happened. So the light bulb is not lighting up, so we know there are no ions in the solution. So I want you to draw what's in that beaker. Just draw the Mickey Mouses. You're going to get so tired of drawing the Mickey Mouses. Sorry, it's a necessary evil. So when you're drawing your liquid, a lot of you, I saw on the test or even on the group quiz, y'all were drawing them all in the same direction, and it looked so perfect that it almost looked like it was a solid, all right? So you need to purposefully make these random, because that's what a liquid is. Closer together than a gas, but kind of randomly placed. So you don't want any of them floating up here, because that indicates it's a gas. You want them all down here, but we want them randomized, all facing different directions. Does that kind of make sense? Yeah. Well, for solid, we're going to align them according to their partial charges. So yeah, you're going to want all the positives and negatives to be next to each other. And you can that kind of does exist in liquids as well, obviously, but it's not something they specifically look for. Did that answer your question? All right. So that's what's in that beaker. That was exciting. All right, this next beaker is going to be a 1 molar potassium iodide solution. For those of you at home, this is a beaker that is a clear solution. There is nothing, whoops, that's the wrong one. There is nothing floating around in it, so it's fully dissolved. So what do we expect to happen when we put the light bulb in this? It should light up. Why? It's a fully dissociated solid because why? How do we know? Potassium is a group 1, and all those salts are soluble. So even though this dissolved, it also dissociated into ions. So let's take a look. Okay? Kind of cool, right? All right. I'm going to put that in here. It's my little rinse thing. All right, so what do we see in this beaker then? Water, and we're going to exclude the water, and we're not going to solvate all these ions, but what's making the electrical current? K pluses and I minuses. So you can put, seriously, pen? Oh my gosh. I wonder if my pen is just dead. It's not. K pluses and I minuses in a 1. I want them in a 1-to-1. I don't care how many you put, but for every 1 K, you better have 1 I. And they need to be random. Not quite as random as I'm doing. Anyway, 1, 2, 3, 4, 1, 2, 3, 4. All right. Okay, so that's what's in that beaker. All right, let's go to our next beaker. In this beaker, we're going to have 1 molar PbNO32, lead 2 nitrate. So what do I expect will happen in that beaker? What? It'll light up. Why? Because why? NO3 is soluble, right? I'm just getting this really rinsed. All nitrates are soluble, and so that is this guy right here, lead 2 nitrate. Let's see. Lit up. So what do we have floating around there? Lead at a 1-to-1 ratio? No, we have lead ions and nitrate ions. For every 1 lead, we have 2 nitrates. So for every lead, we have 2 nitrates. All right. Okay, so that's what's in that beaker. All right, now we're going to get crazy, and I want you to take a minute to tell me what's in there. I'm going to mix beaker 2 with beaker 3. What am I going to do when I do that? I'm mixing Ki and PbNO3 too. So what do you think the best thing to do to figure out what's in there is? Write a reaction. Go ahead and do it. And you tell me what we can expect to see in this reaction. I'm not talking about the lighting. The lighting, this is not a piece of equipment we can really differentiate concentration. I want to know what is going to happen in the reaction. Lead 2 iodide. So my two products of this reaction will be what? And what about lead iodide? What's special about it? It's a solid. So, you think I'm going to form a precipitate when I mix these? Me too. Otherwise, my faith in chemistry will be ruined. Here we go. I don't want to fill it up too much, but all right. See that? Okay. Will it light up? I made solid. Will it light up? Are you sure? Why is it lighting up? What were those ions called? Potassium and nitrate, what were they called yesterday when we did our equations? Yeah, these are my spectator ions still wreaking havoc. And it's kind of hard to tell, but it is a little bit lighter. Like less of the bulb, I can see there's more dark on the bulb. So the light is a little bit less than it was. Can anyone tell me why? Because less what? Right, why? So some of those ions we had originally formed a solid, and that's what now is, that's less ions contributed to the sea of ions that's causing the current. All right, so what do we draw here? Well, we have, what's our solid called again? So what I would do is just like do little circles and do PbI2. I'm not going to have you draw these lattices of these crystals. Just to kind of indicate we've got a bunch of solid in there now. And I didn't tell people at home, the color, this was a bright yellow. Lead iodide is a bright yellow precipitate. And I mean bright. All right, and then what do we have floating around causing conductivity? Potassium ions and nitrate ions. Okay. I'm just going to go crazy with all the ions. All the ions. All right, so that's kind of what we have visually going on. Because if I let this sit, it's already starting. Can you see it settling at the bottom now? Yeah, I'll leave it here till the end of class. And it won't totally clear up, but we'll get some more settling happening. Okay? All right, now the last thing I'm going to do is not very exciting, but I need to make a point because it seems like no matter how often I try to knock this concept home, we still get students who just don't understand it. So I'm going to rinse off real quick. I should not. This is freaking me out because this is like live electrical whatever, and I'm just like throwing water everywhere. Okay. So this is DI water, right? We know it doesn't light up, correct? What I'm going to do now, I've got some little PbI2 floating in there now. Cross-contamination. I am going to put in, this is sugar. Put in some sugar. Stir it around. Most of it will dissolve, but I put a lot in there and the water's not very warm. So I'm going to get it to dissolve as best I can. Da-da-da, da-da-da. So the sugar's dissolving. When I put this in here, will I get a light? A dim one? So there wasn't a light before, but when I put the sugar in, you're saying I should get a dim one. It's not because of its carbon. It's because why? It's a covalent compound. So sugar dissolves because it's polar, right? Does it break into ions? No. The only way you can get a current going through this is for things to break into ions, not for things dissolving. It's for the things that dissolve that bust into ions, and sugar does not dissociate. So you can see here, it is not conducting any electricity. Okay? All right. I'll just leave that. That would be beaker 5, yeah. So I'm not doing a beaker 6. So in beaker 5, go ahead and just draw little circles of sugar, and no conductivity happened. Ooh. So we did C6H12O6 in water. So we just have a bunch of sugar molecules floating around with the water. I'm going to put a couple waters in here just for fun, just to make it a little more interesting. And if we look, our sugar does not conduct electricity, so no light went off on this. All right? So I hope that helps give you kind of a visual representation when we talk about solubility, when we talk about net ionic equations, what's actually going on. Okay? So now we're going to do some titration calculations. And they're the exact same calculations we have been doing, except it has the word titration in it, or it talks about a sample being neutralized by another sample. So y'all did titrations. If you took pre-AP, you did titrations last year, a titration. And anybody remember kind of what the setup was like? Yeah. Not rice table, no. Yeah, you did. You had those long glass burette tubes. And so what your goal was to find the concentration of an acid. And you had your acid in a beaker, and you had the base, or the sodium hydroxide, in the burette, and you dripped it into the beaker until you saw a change in color. That was the point of neutralization. Okay? So then you figured out how many mils was needed to neutralize that acid, and from there you could figure out the concentration of the acid. So we're not doing that just yet physically. I want you to get comfortable with the calculations before we actually, I hate throwing people back there and you not knowing what the calculations mean. You just do them. This way, I know you know how to do the calcs, and we'll apply them eventually. So here it says, calculate the molarity of sulfuric acid, in which is neutralized by 18.5 mils of 0.750 molar sodium hydroxide. So I know this is a titration kind of problem because they're talking about a sample that I'm neutralizing. First step I always want to do is what? Balanced equation. So, and I'm going to write down some things along with it. So I am looking for the molarity of sulfuric acid in a 20 mil sample. I know how much I had, which is neutralized by sodium hydroxide. Sodium hydroxide was 0.750 molar, and I used 18.50 mils of it. What is my reaction going to be? This is acid-base, like most titrations are, not all, because there's redox titrations. In this titration, it is a neutralization scenario. So what do we make? Water and Na2SO4. before. So the only reason I'm doing these products is because I have to balance the equation in order to work with the reactants. I got to know their mole ratio. So I need 2 of those, and I need 2 of those, and now that's balanced, okay? All right. So there's always 3 steps to solving these kind of titration problems. And I like just pointing the 3 steps out because it's always the same. And your first step is to find the moles of the known. There's always one of the substances you know everything about. You're using it to find something out about the other. So which one of these 2 substances in this problem is the known? Sodium hydroxide. So you're going to use whatever information they give you about the known. Sometimes it's moles and molarity. Sometimes it's just grams. Whatever information they give you, you're going to find moles of the known. And then the second step is to use stoichiometry to find moles of your unknown. The unknown is what we're trying to find stuff out about. So what is our unknown in this problem? Sulfuric acid. And again, this is always going to be based on the stoichiometry of the reaction. And then your final step will be to find what you're looking for. That's not always going to be molarity. Sometimes it's grams, sometimes it's mils. It could be a lot of different things. So I never give a definite thing here. It's find what you're looking for based on knowing moles of the unknown. So there's a couple ways we could do this. We could do this step by step, find the moles of known, then do a separate calc, find the moles of the unknown, and then do a separate calc, find what we're looking for. And I'm okay if you need to do that, but we can also do this in one-dimensional analysis. What do you guys as a group prefer? Because I'm not going to do both in class. One-dimensional analysis? All right. We're going to still do these 3 things. What I like about you knowing this is we start with this one in our dimensional analysis, leading to this, leading to that. So we're going to start in our dimensional analysis just like we did yesterday, finding the moles of something are known from molarity and knowing the volume. What do I do first? I'm doing a dimensional analysis. Do the milliliters first. Can we convert that to liters? Are we cool with that? Can I do that in the head, or do I need to write it out? All right, 0.0185 liters. I'm going to start with that liters. Everyone see what I did? Now, again, my goal is to find moles of the known. What do I do with that molarity to find moles of the known? Yep, 0.750 moles per 1 liter, because that's what molarity is. So now my liters cancel. So I've got moles of NaOH. My next step is to find moles of the unknown. What do I do now? Mole bridge, mole ratio. For every 2 moles of NaOH on the bottom, I have 1 mole of NaOH up top. So my moles of NaOH cancel, not moles of NaOH, shoot, 1 mole of H2SO4 up top. So my moles of NaOH cancel, and now I'm in the moles of the unknown. The final step then is to find what you are looking for. We're looking for molarity. I'm in moles of H2SO4. How do I find molarity? Divide by liters, and how many did I use, and how much was in my sample? I'm going to put it down here because moles per liter is molarity. So tell me what y'all get, and we'll see if it matches my number. Yep, I got 0.348, but 0.347 is close enough. 0.347 moles per liter. That is the concentration of my H2SO4. So again, it's always the same steps. Moles of known, moles of unknown, find what you're looking for. All right, let's do another one. It's going to have a little bit of a different twist. Not a hard twist, just something different. How many grams, grams of barium hydroxide are contained in 25 mils if 16.52 mils of 0.850 molar HCl. So I'm mixing that with HCl. I'm mixing it with 16.52 mils of it, and it had a concentration of 0.850. How many grams of that barium hydroxide then would be required to neutralize this sample? So what are my two products? Water and BaCl2. So I need 2 here, and then I need, that's it, right? Yeah. No, I need 2 waters. Okay, so it's going to be the same thing, known to unknown. First step, find moles of known. So what's my known? HCl. I'm going to start with what? Liters, 0.01652 liters. I need to get to moles of the known. Moles of the known, moles of the known. Let's put phones away. .850 moles per liter. And then, and this is moles of HCl. So now I've got to get to moles of unknown. Stoichiometry. For every 2 moles of HCl, I have 1 mole of BaOH2. Now the last step, is it asking me for molarity? No, it's asking me for grams. Did I need to use that 25 mils? No, they will oftentimes give you extraneous information. So what do all we need to do to convert this to grams? Molar mass. This is what the find what you're looking for statement refers to. It might not be molarity. 171.35 grams is the molar mass. Tell me what you get so I can see if we match. One, two, three, four, 1, 2, 3, 4, 1, 2, 3. So 1.20 grams of barium hydroxide. Good. So do you see how they're similar? It's always the same. Moles of known, moles of unknown, find what you're looking for. Okay? So those are only 2 kind of titration-y problems we're going to do. Well, I lied. The number 15 will be as well. But this one right now, we don't have a lot of work to do on this one. I just want to check and see if we can get the concept of this and see if someone can explain it to me. It says 25.0 mils of 0.625 molar HBr is mixed with some NaOH, and it's 42.0 mils of that, and it's 0.352 molar. Will the resulting solution be acidic or basic? This is going to be balanced with 1 to 1 to 1 to 1 because everything's plus or minus 1, so that's a balanced equation. So I want you guys to tell me, what do we think? What's going to make this thing? I thought this was a neutralization reaction. Why would it be acidic or basic? I would say it wouldn't be either. Hang on to that. More of one of the products. Well, those are neutral products. Limiting reagent is key. Can you explain more? It is a limiting reagent issue. Ella. Perfect. She said it perfectly. Good job. Whichever one of those 2 is in excess is going to be floating around as an acid or a base, right? That's going to dictate the pH. Whatever is limiting is going to be turned into this neutral product, this neutralization product. these neutralization products. So that's the key. Whichever is in excess dictates the pH. All right, so how do I find limiting reagent? I always convert to moles. So let's do I'm going to have you all do this in your head, not in your head, but we don't have to write it down. 0.025 times 0.625. We're going to change that mils to liters. I got 0.0156. All right. And then how many moles of NaOH do we have? .0147. Okay. To find limiting reagent, then we then take into account the coefficients, right? But this is 1-to-1. So which one is going to be in excess? HBr. So this is in excess. This is the limiting reagent. So HBr, excess, means what? Acidic or basic? Yep. So again, if I were to draw that beaker, I would have HBr floating around in the beaker. And it would be, would it light the thing up? Why? Strong acid. You still, the HBr is floating around, okay? All the NaOH is used up though. However, what do we have on the product side that's also floating around in ions? This is floating around in ions too. So you get conductivity from the excess acid, H plus and Br minus, and the Na plus and Br minus from him. Yeah. In ions, right. When you have a bottle of hydrobromic acid that's in a liquid solution, it's all ions because it does not stay together because it's strong acid. Okay? All right. This next problem, this is our Big Daddy grand finale problem. We're going to do a pre-lab problem in a second. Not for the next pre-lab, for one way down the road after this. But as far as this unit goes, this is putting everything together. This is the super sexy problem that if you can do this and you get to have a clear understanding of it, you're going to be totally fine. So the hard part about this is like getting your data organized and trying to figure out what you're looking for. So let's just read it. It gives you an equation. Potassium dichromate in an acidified solution, meaning this H+, is frequently used to determine the concentration of Fe2, this guy. So that's what we're doing. We're trying to find the concentration of Fa2. A solution of dichromate is prepared by dissolving 6.45 grams, 425 grams, of K2Cr2O7 in 800 mils of water. A total of 21.35 mils of this is required to reach the endpoint in a titration of a 250 mil sample of iron plus 2. Determine the concentration of iron 2. A lot of information, right? So let me jot a couple more things down. We know that the sample we're trying to find the concentration of, how much of it did we titrate? Iron plus 2. How much of it was neutralized or titrated? 2. You guys have to read the problem. 250 mils sample containing iron 2. So that's our unknown. At the end of the day, that's what we're trying to find information about. It also said that a total of 21.35 of the dichromate was used. So our dichromate is supposed to be our known. What are we missing from all? Think about the problems we just did. What should we know about that dichromate solution? We need its molarity. Okay? So what we did here is we made what we call a stock solution. We made this stock, put it in a burette, and titrated 21.38 mils of it. We didn't use all 800 mils. We used 21.38 mils of it. So what I need to do first, simply enough, is find the concentration of, now notice, what did I take grams of? Potassium dichromate, not just dichromate. So find the concentration of our potassium dichromate, meaning find the molarity. So can we do that? All right, how do we start? Grams, okay. 6.425 grams of K2Cr2O7. And convert that to moles. For every 1 mole, we have, I will give it to you, 294.2 grams. All right. So now I have moles of K2Cr2O7. How do I convert moles to molarity? Are you sure I don't divide it by 21? Yes, no.
Yes, don't do that.
Don't do that because we made 800 mils in a big volumetric, okay? And then we used that, and of that, we used 21.35 of it after the fact. So what do I put down here? 0.8 liters. So this will give me the concentration of my stock solution, and it comes out to be, I got 0.0273. All right. Now, hang on a second. This is the concentration of potassium dichromate. I will say it is equal to the concentration of dichromate, but why? I don't want you to just assume it's equal. I want you to know why is it equal. We need just the concentration of the chromate ion. This is potassium dichromate concentration. Why are they the same? For every 1 mole of potassium dichromate, I have 1 dichromate. All right? So if I needed the moles of potassium, what would I do? Multiply by 2. All right? So anyway, we know then that this now is this concentration that we're looking for, 0.0273 molar. So now it's a problem like we just did. Now we can actually start the problem. It's kind of crazy. So to start the problem, I don't want to get rid of my... All right, find moles of known. What's our known? Dichromate. So how do I start with my stoichiometry? All right, dimensional analysis, sorry. Convert those mils to liters, so 0.02135 liters. I got to get to moles of known. What do I do? Right now, I am in liters of dichromate. I've got to get to moles of known. Yes. 0.0273 moles per liter of Cr2O7 negative 2. Now I am in moles of Cr2O7 negative 2. Now what do I do? Mole ratio to get to the unknown. Moles of known, moles of unknown. For every 1 mole of Cr2O7 negative 2, I have 6 moles of Fe plus 2. Now we have moles of unknown. Now we're supposed to find what we are looking for. How do we do that? Divide by 0.25. That 250 mils, 0.25 liters. Okay? All right, what is our... Can I get a second? Awesome. All right, so that is of the iron plus 2. So this incorporates everything you learned. How to find out molarity with solution making, understanding the concept of stock. That's something we use and put into the burette. Okay? When we start to physically do this stuff, it'll make even more sense. but make sure you know how to do this problem. If you need to come in, I'll sit with you and work through it again, but this is not a problem you can just go, oh, well, I'll miss one on the test. Can't do that. Got to know it. All right? Okay, last thing we're going to do, it's going to take just a second. This is a pre-lab question that you're going to run into, not in tomorrow's lab. You'll remember it when we get to, it's called the bullet lab. That's hard to forget. The point of this lab we're going to do, you're going to find the percent of copper in a bullet casing, which is made of brass. So part of that is dissolving your bullet in nitric acid to create the copper ions. So you're going to dissolve, and it's not an actual bullet, it's the casing, so you won't die. Don't worry about it. I, however, may die when I go to the gun range to ask for bullet casings. I'm like, hi, bam, bam, and I'm like falling to the floor anytime I hear anything. I hate going there. But anyway, so part of doing this, and this is just going to give you another twist on finding what you're looking for. We're not always looking for molarity. Sometimes we're looking for volume. Okay? So in this problem, we're going to start with 0.345 grams of copper. So what we're basically going to do is, that could be the mass of your bullet casing. And in order for us to make sure we react it with enough nitric acid, we have to pretend the whole bullet is copper, even though it's not. We're going to make sure to get it all reacted. So we're going to assume that the whole 0.345 bullet casing is actually copper. And our job is to figure out, okay, how much of this crazy concentrated nitric acid does DEMO need to add in order to react all of my bullet? So we have this 16 molar, and we want to know what volume, and I'd rather convert it to milliliters because that's easier to measure, is required to react all that copper. So this is just your ordinary moles of known, moles of unknown, find what you're looking for. All right, so moles of known, what's our known? Copper. So we're going to start with 0.345 grams of copper. Okay, and you guys need to be writing this down because when this pre-lab question comes up and you say, how do we do it, I'm going to say, look at your notes. How do I convert this to moles? For every 1 mole of copper, I have 63.55? 63.55 grams of copper from the periodic table. Now what do? Mole bridge, 1 mole of copper, I have 4 moles of nitric acid. Now what do? Who can figure this out? Fun liters, how? I have the molarity, right? You need to remember that this equivalency can be placed right side up or upside down in your dimensional analysis. So I have 16 moles for every 1 liter. And now I know, though, that every 1 liter, because I'd rather measure it in mils, is 1,000 mils. So how many mils am I going to have to add to this tiny, tiny bullet casing? It's actually way smaller than an actual bullet casing. So your bullet casing will be well above 2 grams. But how many mils do I add? Sorry? 1.4 mils of nitric acid. Not very much, huh? It's a really cool reaction, though. We have to do it under the fume hood because it produces nitrous oxide, which is a very colorful brown gas that will, well, it's actually nitrous dioxide. Change that. But it'll knock you out. So, oh, really? If you don't, people who don't have fume hoods, they have to go outside to do this. Can't do it in a room. No, no. That would be remiss of me to let that happen. Okay, so that's the last lecture of the unit. We're going to be labbing it up for the rest of the unit. So